second week. So in last lecture we covered the steady state error. So steady state, definition of the steady state error and the basic formula and their derivation, how to find the steady state errors. So because our derivations most of the times in frequency domain, so definition of the steady state error is in time domain. So we apply the final value theorem and find the value of the error signal at time equal to infinite. So this is the first lecture of the week. In last interactive section, there is no specific query from the students, so uh, try to understand the lecture, and if you have any further queries you can email or text me through the CR before the interactive session, so we can discuss in detail in the next interactive section. So in this lecture, most of the basic formulas is already derived, so we'll try to apply these formulas in some numerical problems. Last lecture we derive some error constants, and first of all we start from the basic definition of steady state error and the basic static error constant definitions, and if we applied on the different system types uh, with different inputs, what will happen. Let's start with a summary and then apply these relations to the numerical examples. The linear control system is divided into three major parts. First one is the modeling. In modeling, we covered how to mathematically model mechanical or electrical systems or electromechanical systems, and also representation of these systems in time domain and also in S domains. If we represent the systems in differential form, then how to convert the differential form by applying the Laplace transform into a S domain representation. And also there are other representations. After covering the modeling, we uh, start the analysis part by a discussion with the discussion of transient analysis. In transient analysis especially, we derive the specific relations to define the specific parameters which will be helpful to design the systems. So first order and second order transient analysis is we study in deeply, and then is the stability. And next part is the steady state error. This steady state error is also helpful to design the systems. If there is error, then how to remove this error and make the systems error free. So let's see. We find the steady state error in terms of closed loop transfer function. For example, if we have a closed loop transfer function T of S, which is given, and R of S is the input or reference value, and C of S is the output or control value. And error signals we can find through the difference of input, and if we take the input from this terminal and it is added with this junction with plus sign, and taking the negative sign of the output of the control value, then this error signals definition is equal to input times 1 minus closed loop transfer function, and this S actually representing to satisfy the final value theorem. So steady state error, which is already derived at time equal to infinite, or in S domain it is equal to S times EFS. So here we find the EFS and the whole relation. If value put here, then we can find the steady state error by this by using this relation. And similarly, if we have an open loop transfer function, for example, in this case GFS is representing the open loop transfer function, and RFS is the input value and CFS is the output or control value, and we derive this relation error signal in terms of the input value by 1 plus the open loop transfer function with unity feedback. Our consideration is unity feedback. If there is no unity feedback, then we can take the value of the transfer function, and to find the steady state error in this format, we are derived. If we put these values here in this relation in the definition of steady state error, which is the time domain discussion, so we can find the steady state error by using this relation. So these are the summary for different type of static error constants. For the if we take directly open loop transfer function and apply the limit f s approaches to 0, then this constant is the position constant. And we observed in the case when there is a step input, then we have value of corresponding steady state error is 1 over 1 plus this constant. And similarly for the velocity constant, and this uh, velocity constant is defined as s times the open loop transfer function as at s is equal to 0. And this observed when we apply the RAM input, and there is the steady state error is a 1 over the constant. And similarly is the acceleration constant, and this acceleration constant is defined as s square times the open loop transfer function as at s is equal to 0, and corresponding steady state error is equal to 1 over constant when there is parabolic input. I am taking the same example once again. For example, in this case we have open loop transfer function which is equal to 120 times s plus 2 and divided by s plus 3 times s plus 4. It means in open loop transfer function there is 1 0 at minus 2, and there are two poles at minus 3 and minus 4. If we uh, take the input r of t is equal to 5 u of t, then according to the definition we required in S domain to just take the Laplace transform, which is equal to 5 over s, and substitute these values in the definition of steady state error. Because this is a unit step, so in steady state error is the for unit step. It is not a unit step, it is a 5 time of the unit step. So it is 5 over s, and times the s, which is according to the definition, and this s is cancelled out with this s, and here we record open loop transfer function at s is equal to 0. So just value take the value s is equal to 0, and we have the open loop transfer function is 20. So finally we find 5 over 21, which is the constant error. If we have type 0, it means there is no pole at the origin. It means if we compare with this generalized form, there is no pole at the origin, and it is a second order system. So for second order system, and type 0 systems, if we apply the step input, we have the constant steady state error. And similarly, if we take the RAM input, if we consider the RAM input, then Laplace transform of this RAM is 5 over s square. So this is the open loop transfer function. Once again, the same open loop transfer function. in in this case, we are changing the input value. So first we have applied the unit step, and now we are applying the RAM input. If we apply the RAM input, then definition of steady state error is equal to s approaches to 0 s r of s divided by 1 plus g of s. Okay, in this case we have s, or r of s is 5 over s square. One s is cancelled out with this s, and 1 plus g of s. Here we have the limit. And then next step is s approaches to 0 and it is 5, and this is taken in the denominator part. Then we have s plus g of s. If we apply the limit, this s is approaches to 0 and there's no influence on the overall steady state error, so only influence is this due to this one. Then we have to find the value of this whole value, this one, using the g of s open loop transfer function. And then we find, for example, even g of s at 0 is, in last case we find the 20, but this s make the term is 0. So something is 0 is infinite. It means if we take the RAM input with the same step, if we excite with the RAM input, then steady state error is changing. In last case we find the some fixed value error, which is 5 over 20 and 21, but in this case we find with the same transfer function, we find that steady state error is infinite. And similarly for the parabolic input, same transfer function is we excite with the parabolic input, then the steady state error is infinite. Again, just try to draw the relation. In S domain, s approaches to 0, s or r of s is 10 over s cube over 3, so 1 s is cancelled out, and we have 1 of g, and this is steady state error. And limit s approaches to 0, so 10 over s square plus s square g of s. So once again, if we apply the initial value s approaches to 0, this term goes to 0 and this term also goes to 0, and something over 0 goes to infinite. So this is the infinite value. It means if we find the steady state error for the same systems with step input, error is constant, but if we change the type of the input, which is RAM input, same systems gives the infinite steady state error, and similarly for the RAM input. So let's find the impulse response of the same systems, which is type 0 and second order systems. So Laplace transform of the impulse function is 1, and if we find the steady state error, which is the limit s approaches to 0, s times RFS 1 plus GFS. Here RFS is 1, so we have this type of function. If we apply the limit s approaches to 0, and this s make the function 0, and value of g of s at s equal to 0 is 20. So ultimately we find the zero error, which is very interesting. In the whole example we are changing input type. So let's see what's the summary of this topic. So let's summarize the whole concepts which we find here. We have an open loop transfer function which is type 0 and second order systems. If we apply impulse function, then response of this impulse is 0 in steady state. And similarly, if we apply the step value, then the steady state error is constant. If we apply the RAM input, then steady state error is infinite. And similarly, for the parabolic input, steady state error is infinite. So it is interesting case. Then it's again you have an other topic to think about it. If we take the type 1 systems, it is your real-time assignment. Try it during the video lecture. Just take the type 1 here. Just it's a second order. Just if we take s raised to power here, no, one pole, we are adding one pole at the origin. No, it is a third order systems and type 1 systems. What will happen? Let's try and find the result and discuss with in the interactive session. If you have any query related to this one, you may ask me. And similarly, if we increase the type of these systems, for example, in first case you take the type 1 systems and similarly take the type 2 systems and apply these inputs for these two examples, and what will be happen in terms of steady state error. Try it. Now this table once again make you more comfortable if you closely observe these terms. First of all, we have to define these constant terms. If we apply the step input for open loop transfer function, then this term GFS is the constant, and this constant is the position error constants. And similarly, if we apply the step input, then we have this is equal to constants for the same systems, and similarly for the acceleration constant, we have the definition of system is like this one. But now our concentration now focused on the G of S. If we change the type of systems, for example this is type 0, then definitely we find the some constant value. If it is type 1, answer will be different. And similarly, if it is type 1 system, then this S will be cancelled out with that one, and overall we find the some DC value or constant value. And similarly, this is also a constant if we take the G of S is type 2 systems, then definitely this answer is constant for parabolic input. So this is the summary to try to understand the both terms in a combined way, and it will be helpful to understand the remaining part of the lecture. Okay, let's see another example from your textbook, that we have open loop transfer function. It is the type 0 and third order systems. So we have to find the static error constants, and from there we have to finally we find the steady state error. So in let's see we'll take the uh, open loop transfer function, and if we want to find the position constant. So position constant is definition of the position error constant is just take the open loop transfer function here. Complete open loop transfer function is this one, 500 into s plus 2 into s plus 5. There are two zeros at s equal to -1 and s equal to -2 on the real axis, and similarly there are three poles. First pole is at s equal to -8, and second pole is at s is equal to -10, and third pole is s is equal to -12. So these poles with a fixed value of k, for example in this case we consider this value is k, and then we have to find the value of different static error constants. First of all, find the position error constant. Definition of the position error constants that we derived in the last lectures, that if we find the s of g of s and apply the limit s approaches to 0, then in our example if we apply 500 times 2 times 5 divided by the 8 times 10 times 12, then we have some constant value. And similarly, if we want to find the velocity constants, so velocity error constant definition will be s times open loop transfer function. If we apply here s to raised power 1, which is in the definition of the velocity constants, then if we applied the limit s approaches to 0, then this s make the whole term equal to 0. It means the answer is 0. Similarly, if we take the acceleration constant, then there is a s square in the product form of open loop transfer function, and there is a limit s approaches to 0. So once again this answer is 0. It is very important conclusion from here that if we have type 0 systems and we want to find the error constant, so position constant is have some constant value, and velocity and acceleration are the 0 constants. So this thing make the steady state error like this one. So these are the error constants as we find. So apply in the definition of steady state error. So it is 1 over 1 plus that constants. So for type 0 answer is steady state error is 0. Similarly, if we want to find the steady state error uh, using the velocity constant and acceleration constants, then it's indicate toward the RAM input and the acceleration input, and this and the errors are the 0. So let's take the second part of the example. In second part, almost a similar type of relation of the transfer function. For example, we have some constant value 500 and there are one zero at -2 and second zero lies at -1 and third zero lies at -6. The whole zeros are lies on the left half plane, and similarly there are four poles. Instead of three poles there are four poles, but interesting case is here that one pole is at the origin. If it is at the origin, what will happen with the errors and what will happen with the static error constants? So it's actually, if the system is stable, then we have to find the value of the steady state error. If the system is unstable, then it is we are unable to find the steady state error. So this our discussion is still toward to understand the concepts of stability and the with different type of input and the different uh, system type all together, and definitely it will be helpful to design a stable to design a controller for the stable systems and what type of input will be suitable for that type of systems and so on. So let's once again -8, -10 and -12 are the positions of the other poles and one pole is at the origins. Then first of all it is our task to find the error constants. Position error constants definition is simple. Just open loop transfer function and apply the limit as approaches to 0. In this case, this s in this case, uh, if the type is type 1 system, then 1 over s, which is the integration, one integration, make the position error constant infinite. Position error constant make the infinite. And similarly, if we have the we want to find the value of the velocity error constant, then velocity constants parameters according to the definition is equal to s times open loop transfer function, and this s is definitely cancelled out with s here, and the whole thing make is a some constant value and by applying the limits s approaches to 0. And similar case is here when we apply we want to find the value of acceleration constants, which is s square times the open loop transfer function, and open loop transfer function is type 1, so 1 over s is cancelled out this 1s and remaining term is constant at s approaches to 0. So this s make the whole thing equal to 0. So now this acceleration constant is 0. For type 1, kp is infinite, kv is some constant value, and ka is 0. By using these constant values, how to find the steady state errors in the same examples. Here kp is infinite and kv constant and k is 0. Then steady state error for this systems first is 0. So if we take infinite in the denominator part, then one something over infinite is make the whole value is 0. And similarly this kv is some constant, so something over constant is again a constant, and in the acceleration by using the accelerating constants we find that the steady state error is 0. So this is the step input and this is the RAM for RAM input, and this is for the parabolic input. So next example, in this example, we have to find the first of all error constants and then corresponding steady state errors. Again, this is the type 2 systems. There are two poles at the origin, there are double integration. So there are total 5 poles in open loop transfer function, and 3 poles are lies on the definitely on the left hand half plane and 2 poles at the origin, and similarly there are 5 zeros, all zeros lies on the left half plane. And first of all we have to find the positions constant. Position definition of the position constant is just take the open loop transfer function and apply the limit as approaches to 0. So if we apply the limit as approaches 0, in this case the whole terms is make infinite because there is denominator s to its power 2. So if we take the s in denominator part of g of s, then we find the value of kp is infinite, something over 0 is infinite. And similarly for the velocity constants, so velocity constant, to find just multiply s, which is in the definition of times the g of s. Just one s is cancelled out one s, but still there is one pole is at the origin in the definition of kV, so this thing make is infinite. So if we want to find the acceleration constants, then acceleration constant in this case is this g of s, uh, 1 over s square times the whole terms. So 1 over s square is cancelled out with the definition of the acceleration constants s square, and the remaining term make constant value when we apply the limit s approaches to 0. And if we have set type 2 systems, then acceleration constants is constant, but velocity constants and position constants both are infinite. So how to find the corresponding steady state errors? Okay, for type 2 systems, if if we want to find the steady state error for uh, uh, by using the position constant, then 1 over 1 plus kp is some infinite, so 1 over infinite make the term equal to 0. So steady state error is 0 in terms of kp. It means if we apply the step input to the transfer function with type 2, then we have steady state error is 0. And similarly, if we apply the RAM input, then once again steady state error is 0. But if we want to find the steady state error by using the parabolic input, then steady state error is not 0, it is constant value. This is the whole summary you have to make through this example, and this conclusion can be deduced from also from the table. So in this example, if the type 0 system, then we have the position constant is constant, but velocity and acceleration constant are 0. And similarly for type 1 systems, kp is infinite and kv, velocity constant is constant and acceleration constant is 0. And similarly for type 2 systems, kp is infinite and kv is also infinite, and acceleration constant is constant. And the corresponding error can easily be derived or explained through this table. First of all, let's summarize. If we have a type 0 systems, then acceleration constant and velocity constants are 0, but position constant is some constant value. And similarly, corresponding steady state errors are constants, infinite and infinite. It means that if we have a type 0 systems, then we can only apply the able to apply the step input or impulse. If we apply the RAM or parabolic input, then this thing make the systems unstable and there is infinite steady state errors. And similarly, for other cases, if we have type 1 systems, then uh, Kp is infinite, Kv is constant value, and Ka is 0, and corresponding steady state errors are 0, constants and infinite. It means if we want to run the systems error free of type 1 systems, then we only use the step input or impulse function. Otherwise, the if we apply the RAM input, then this thing make there is some error. Maybe there is a error is minimum or maximum, depends on the amplitude or the constant coefficient of the RAM input, but there is some error, but we are unable to apply the like the parabolic inputs, so we cannot excite the system by using the parabolic inputs. And similarly, if we have type 2 systems like this one, then there is a two pole at the origin, then corresponding error constant, position error constant is infinite, and velocity error constant is also infinite, but acceleration constant is some constant value. But correspondingly, if we want to find the steady state error corresponding to Kp, we are there is 0. If we want to apply the step input, error is 0 again. If we excite the system by using the RAM input of this type 2 systems, then again once again the steady state error is 0. And if we apply the parabolic input to the this type 2 systems, then there is error. So if we want to run this type 2 systems error free, then we can use the step input or the RAM input to make the system's steady state error equal to 0. So summary of the whole topic is here. In this first column we have different type of input. For example, unit input and the RAM input and the parabolic input. This is u of t actually only for positive time in region. So steady state error formulas we already derive here. 1 over 1 plus kp, and for RAM input 1 over kv, and for parabolic 1 over ka. So static definitions. So now we consider the type 0 or type 1 systems or type 2 systems. What will happen actually, if there is a type 0 systems, then this constant kp is constant, and velocity constant and the acceleration constant are 0, and corresponding steady state errors are some constant value and infinite and infinite. We are only able to apply the impulse or unit step functions for on the type 0 to run error free. So if there is a type 1 systems, then the kp is infinite, kv is some constant value, and acceleration constant is 0. So corresponding errors is 0 for kp and for step input, and similarly for kv error is some constant value, and for acceleration constant, in terms of acceleration constant, it means for parabolic input error is infinite. It means if we want to run a systems type 1 system error free, then we have to use the just step input. And similarly for step type 2, we can we can apply only step or RAM input to run the systems error free. This is the summary. So keep in mind, it is very interesting situations to understand the systems in a forward way. It means stability and errors are depends on the input and the type of systems. If we change the input or type of systems, error definitely will change. And if the in a reverse way, if the some information is given in terms of some constant value, then we can guess what will type of system is there, what type of input we can apply on these systems to run the error free and so on, and what about the stability and so on. So this is the criteria, and this criteria will be applied, and we will be able to solve different type of examples in a reverse way. If the information is given in terms of kp and kv and errors, then we can guess or estimate the type of systems and the systems characteristics. Same summary in a different way. For example, here on the first column representing the type, and this is the type 0, type 1 and type 2, and this horizontal column representing the different type of inputs. So if we apply the step input to the type 0 systems, then there is to find the steady state error formula is given this one, 1 over 1 plus kb. But if we want to find the step response on the type 1 systems, then there is steady state error is 0, and similarly for the type 2 systems. And if we excite the system by using the RAM input, and we have a type 0 systems, then there is an infinite steady state error. And if the type 1 systems, then there is some constant error, and similarly if the type 2 systems, then the error is 0. And similarly for parabolic excitation, for if we apply the parabolic input to the systems, then behavior of the system in terms of steady state error for type 1 and type 0 systems, steady state error is 0, and the steady state error for the type 2 systems is 1 over ka. It depends on the error acceleration constants. So this is again the another way to observe the table. It's the more simplest table as compared to the previous one. Try to understand and summarize these tables, and now you are able to apply these techniques on any type of example. Uh, so lecture is lengthy, so try to compile the whole situation. So first of all, this lecture again starting with the introduction of some steady state error, and we always discussion of the steady state error for unity feedback systems. And now our main focus in this lecture is to find the static error constants and corresponding steady state error with different type of systems, type 0, type 1 and type 2 systems, and try to make a whole summary in a more condensed way. So try to apply these techniques on different type of systems and make the summary in at in the your own words and in your own format. So it will be helpful in the long run to design the controllers. Thank you so much.